The James Webb Space Telescope has ushered in a new era in extragalactic astronomy. The infrared observatory has already uncovered numerous candidate galaxies that call the Big Bang Theory and our models of galactic development into question. And now, the Webb Space Telescope has caught a sight of the universe's most distant star, which was announced only a few months ago by scientists using Webb's predecessor, the Hubble Space Telescope. The star, called Irondale, after a character in J.R.R. Tolkien's Lord of the Rings prequel, The Silmarillion, was spotted in a Hubble Space Telescope deep field image thanks to gravitational lensing. The star, whose light took 12.9 billion years to reach Earth, is so faint that spotting it in the new James Webb Space Telescope image shared on Twitter on August the 2nd by a group of astronomers using the account Cosmic Spring JWST may be challenging. But how did astronomers detect a single star so far out in space? What distinguishes Irondale from the other stars we see? Finally, and most crucially, how do the recent James Webb observations of Irondale undermine our stellar evolution theories? Keep watching until the end as we attempt to address all of these questions. The light of a star that formed during the first billion years after the universe's beginning in the Big Bang has been detected by NASA's Hubble Space Telescope, the farthest individual star ever observed to date. The discovery represents a significant step back in time from the previous single-star record holder, which was discovered by Hubble in 2018. That star existed when the universe was about 4 billion years old, or 30% of its current age, at a time that astronomers refer to as redshift 1.5. Scientists use the term redshift because light from distant objects is stretched or shifted to longer, redder wavelengths as it travels towards us as the universe expands. The newly discovered star is so far away that its light has taken 12.9 billion years to reach Earth, appearing to us at redshift 6.2 when the universe was only 7% of its present age. The smallest objects previously detected at such a long distance are star clusters embedded within early galaxies. We almost didn't believe it at first because it was so far out from the previous most distant, highest redshift star, said astronomer Brian Welsh of Johns Hopkins University in Baltimore, the primary author of the paper revealing the discovery, which was published on March 30th in the journal Nature. The discovery was made from data collected during Hubble's RELIX Reionization Lensing Cluster Survey program, led by co-author Dan Coe at the Space Telescope Science Institute. Normally at these distances, entire galaxies look like small smudges with the light from millions of stars blending together, said Welsh. The galaxy hosting this star has been magnified and distorted by gravitational lensing into a long crescent that we named the Sunrise Arc. After studying the galaxy in detail, Welsh determined that one feature is an extremely magnified star that he called Irondale, which means morning star in Old English. The discovery holds promise for opening up an uncharted era of early star formation. Irondale existed so long ago that it may not have had all the same raw materials as the stars around us today, Welsh explained. Studying Irondale will be a window into an era of the universe that we are unfamiliar with, but that led to everything we do know. It's like we've been reading a really interesting book, but we started with the second chapter and now we will have a chance to see how it all got started, Welsh said. According to the researchers, Irondale is about 50 times the mass of our Sun and millions of times brighter, rivaling the most massive stars known. Hubble was able to discover Irondale because the light from the star was lensed by the galaxy cluster WHL 013708, which sits between us and the star. The enormous cluster behaved like a magnifying glass, magnifying the light of the star by 1,000 to 40,000 times. Even a dazzling, extremely high-mass star would be hard to detect at such a long distance without the natural magnification provided by WHL 013708, a massive galaxy cluster located between us and Irondale. The galaxy cluster's mass warps the fabric of space, forming a powerful natural magnifying glass that distorts and considerably amplifies light from distant objects behind it. Thanks to the rare alignment with the magnifying galaxy cluster, the star Irondale appears directly on, or extremely close to, a ripple in the fabric of space. This ripple, known as a caustic in optics, gives maximum magnification and brightness. The effect is analogous to the rippled surface of a swimming pool, creating patterns of bright light on the bottom of the pool on a sunny day. The surface ripples work as lenses, focusing sunlight to maximum brightness on the pool bottom. Because of this caustic, the star Irondale stands out from the overall glow of its home galaxy. Its brightness is multiplied 1,000 times or more. At the moment, astronomers are unable to tell if Irondale is a binary star, despite the fact that most big stars have at least one smaller companion star. It is the most distant and oldest star known so far. It is located at a distance of 28 billion light-years from Earth. It is nearly twice as far as the previous record holder, Icarus, MAX J1149 Lens Star 1. Irondale is located in the center of the constellation Cetus, above the imaginary line linking Zeta and Theta Cetae. Even the largest amateur telescopes cannot see the star due to its apparent magnitude of 27.2. Irondale's host galaxy, catalogued as WHL 0137ZD1, was nicknamed Sunrise Arc because gravitational lensing bent its light into the shape of a long crescent. The two red dots visible on either side of WHL 0137 lensed star are both the same star cluster whose light has been bent into two separate images that mirror each other. When the starlight from Irondale was emitted, the star was only 4 billion light-years away from what became the Milky Way galaxy. As the universe expanded during the 12.9 billion years that it took for the light to reach Earth, the star would now be 28 billion light-years away. Irondale is a hot blue star with a mass between 50 and 100 times that of the Sun and a surface temperature of at least 20,000 K. Its properties are unknown beyond that. Stars with such a massive mass do not live for very long. They swiftly deplete their hydrogen supply and evolve away from the main sequence to become supergiants. Irondale likely went out as a supernova only a few million years after forming. There is a slim chance that Irondale is a population 3 star. Population 3 stars are a theorized group of extremely large, hot, and luminous stars that existed in the early cosmos. These stars had nearly no metals in them. They were virtually entirely composed of primordial hydrogen and helium. They are thought to have started the production of chemical elements heavier than hydrogen, which are essential for the formation of planets. Hubble could only provide limited information about this faraway star due to its wavelength constraints. As a result, astronomers used the James Webb Space Telescope to further investigate Irondale's properties. Dr. Brian Welsh of Johns Hopkins University led this study. The researchers examined new images of Irondale collected by Webb's NIRCam instrument in their publication. These images range in wavelength from 0.8 to 5 microns. Irondale was investigated using 8 different Webb filters, each with an exposure period of more than half an hour. The new James Webb Space Telescope observations highlight major points. The first is the redshift of the star. The redshift of far space objects indicates their distance. The dimensionless quantity Z represents redshift. Z equals 0 represents the present time. And as its value increases, so does the look-back time and the distance to the object. New Webb observations confirm that Irondale is located at 6.2 redshift. This figure agrees with Hubble Space Telescope data released in early 2022, making Irondale the highest redshift star yet discovered. The bolometric luminosity of Irondale, or the energy released by the star across the whole electromagnetic spectrum, is also worth noting. The Webb results rule out Irondale being a low-mass star, a brown dwarf star, or a free-floating exoplanet that became gravitationally lensed. Massive stars in our local universe typically have companions, and in many cases more than one companion. While the primary companions are 2 astronomical units away from the star, the tertiary companions can be up to 20 astronomical units away. This means that even if Irondale has companion stars, they will be invisible to the James Webb Telescope due to its low resolution. Another issue is that if the star is 1 million times brighter than the Sun, it will exceed the Humphreys-Davidson limit, sometimes known as the HD limit. The HD limit is the empirical luminosity limit over which no stars, at least in the local universe, have been detected. So if Irondale is verified to be a single star 1 million times brighter than the Sun, we may have to re-evaluate the HD limit and impose additional limits on it. The discovery of Irondale is significant because it could be the first detection of a population 3 star, which astronomers have been looking for decades. Astronomers anticipate that Irondale will remain highly illuminated for many years. The following Irondale observation with the James Webb Space Telescope is slated for December 2022. Irondale's type and stage in the stellar life cycle would be narrowed down if its brightness and surface temperature were accurately measured. Astronomers also believe that the Sunrise Arc galaxy will be devoid of heavy metals that emerge in following generations of stars. It strongly implies that Irondale is an unusual, enormous, metal-poor star. Finding the first stars and galaxies has long been considered a holy grail in astronomy. The discovery of the first generation of stars would help us comprehend star creation and validate the Big Bang model's predictions. In addition, looking for them is like to looking for our own origins. Whatever more we can learn from its spectrum will have to wait a little longer. With the JWST capable of discerning details that the Hubble Space Telescope can't, astronomers might soon be able to glean a few more clues about this new record holder. Irondale's exhausted light has come a long way to get here. Whatever it has to say, we're sure it's worth waiting a little longer to listen to. If you enjoyed this video, make sure to like it, subscribe to our channel, and press the bell icon so that you don't miss any future videos.